Hello, everybody, and welcome to section 3.6, where we're going to talk about the logarithmic function and how to differentiate and how to use a couple of the properties of the logarithmic function to simplify some derivatives. So overall, this section should be pretty short. However, I'll probably still drone on for far too long. But we're only adding on this one extra, we're only adding on this one extra ability of being able to correctly identify and differentiate the logarithmic function. So we still need to remember how to differentiate everything else, right? Polynomials, rational functions, trig functions, product rule, quotient rule, chain rule, all still apply. So we're just going to throw this in the mix. We'll start with the easiest one, which is the natural log. If y is ln of x, then y prime is 1 over x. I just want to take a brief pause here and relate this back to y equals e to the x. Means y prime is also e to the x. And these are inverses of each other, right? E to the x. When I look at that in terms of a function, I get the inverse to be natural log of x. Right? So these are inverses of each other. The nice thing about the exponential function base e, if I look at y equals e to the x, it grows at its own rate wherever you evaluate it. So if I want to know how fast y equals e to the x is growing when x is 10, it's growing at e to the 10, right? Because I would just plug in 10 into the derivative, but the derivative is the same as the original function. So it's the only function that has that property such that it grows at the rate that whatever number you're evaluating it at. And the inverse grows at the reciprocal rate. So if you take natural log of x and you want to know how fast it's growing when x is 10, well, it's 1 over 10. Right? So it grows at the reciprocal of the argument. That's the rate that it grows at. So that's a nice thing about the just kind of relating back and forth between the exponential function and the logarithmic function. But we also saw that if we weren't dealing with base e, which is the natural log, if we were dealing with log base b, where b is, for us, just going to be like some positive integer, not 1, because that would just be silly, then y prime is 1 over x, natural log of b. So this is a log with a different base other than e. It could be base e here. You would just be dividing by ln of e, which is 1, so that's why you don't see it in the first one. But you do see it here because, for example, if you look at the derivatives for y equals b to the x, where b was some number that wasn't e, then you would have something like b to the x times log of b. And again, I say log, I mean natural log. Right? In mathematics, we always are consistent, and we like to use the natural log all the time. If you need a different base, you do the change of base formula. So for me, I'll say log, because these are both logs. Right? This is a natural log, L-O-G. This is a log, L-O-G, so it makes no difference. So we saw that if it was a different base, then we might have to multiply by natural log of b. Here, if it's a different base with the log, we do have to divide by natural log of b in order to get the proper rate. Because if these are different bases, then the log function grows at different rates. And when you encounter the logarithmic function, it looks like this, and it always crosses when x is 1. No matter what the base is, log of 1 is always 0. And so it gives you that 0.1, 0 every time. But it grows at different rates depending on what the base is. Now, if you look at the logarithmic function, it almost looks like it kind of just levels off and doesn't grow anymore. But the larger this value is, the larger this is going to be. This number is going to be rather large, but the derivative is going to get smaller and smaller and smaller, meaning it's growing at a slower rate. So here it grew pretty quickly, it grew quickly, it didn't grow so quickly, it's barely growing, it's not really growing, but it is still growing, and it keeps growing and growing and growing. It just grows so slow. So yes, the larger this x is, the smaller the derivative gets, but it never gets to be 0. If this was natural log of 84 billion, This would be 1 over 84 billion. The derivative is not 0. It's close, but it's not. So it's still growing. This is one of the slowest growing functions you will ever encounter in your math career, probably. I mean, of course, you could create a slower growing function. But as far as the regular functions that we're used to using, this is the slowest growing function you will see in popularity. So now that we've got log functions situated as far as the rate that they grow at, meaning we connect that to the derivative, we also have to look at what happens if we're dealing with the chain rule. So if there is an entire function in the argument, then I have to be a little more careful. And the chain rule says I do 1 over the inside times the derivative of the inside. The faster way of writing it is the derivative of the inside over the inside. Because if I multiply by f prime, it's just going to sit in the numerator, right? So this gives us our derivative using the chain rule. I'll show you an example of this. Let's say if y is equal to the natural log of 4x cubed plus 2x minus 7, and find y prime. All right, so there's a lot more going on inside the log, and we can't break this up. If you're thinking, oh, I know some log properties where I can break it up, log, log, log. No, absolutely not. That's plus and minus. That's not a rule. It never has been, never will be. This is just a polynomial. It has to stay a polynomial. It can't be separated into a bunch of different logs. So in order to find y prime, I now have a function inside. So I have to do the derivative of the inside, which is 12x squared plus 2, over the inside, which is 4x cubed plus 2x minus 7. And that's it. So essentially, we're looking at the ratio 1 over the inside, but then having chain rule kick in and multiply by 12x squared plus 2. If I'm going to multiply by it, I might as well just put it in the numerator to make it save space. So that is our derivative using chain rule, but using it very quickly because it's just a little bit faster to write it out as one ratio. Now, you heard me mention things about properties of breaking up logs. And you're saying, well, I could break that up. Well, you'd be wrong, because you can only break it up if it's multiplication inside the argument or division inside the argument, or if we have a power inside the argument. So I think it's worth noting that if we come back and sort of revisit these properties, then it should all be clear again. If it's multiplication of 2 different arguments inside, then we can break it up. And this works for a log of any base. That's why I'm writing log base b. Like I said, 9 times out of 10 we'll be dealing with the natural log most of the time. If I have multiplication inside, I can break it up with addition of 2 separate logs. If I have division inside, I can break it up with subtraction of 2 separate logs. And one other one that we'll use quite often is if I have a being raised to some power, then I can bring that power down as a multiple. I forgot my b down there. All right, so that power can come down as a multiple of the log. So these are the 3 properties. Again, we do not get properties that have log of a plus b inside can be broken up. We do not get properties of log of a minus b inside can be broken up. These are all you have. They're all you'll ever get. So don't try and manipulate something using logs when it can't be manipulated correctly. So what I mean by using these properties is, let's say we want to find dy dx. If y is equal to, and I'll stick to the natural log of, let's try 3x to the fifth times x plus 2 cubed. All right, if we're dealing with a function like this, now there's nothing wrong with just attacking it and doing, okay, I'll do the derivative of the inside over the inside. When I have the log of a function f of x, that's how I do it. I do derivative inside over inside. That's taking care of my chain rule. Well, the derivative of the inside needs a product rule, and it also needs some chain rule because of that power on that binomial. That's a composition. So it could be a little extensive. Or you can break it up first. Since this is a product of two things, 3x to the fifth and x plus 2 cubed, I could break it up by doing the addition of two separate logs. I can break it up even further if I want, because this is also multiplication, 3 times x to the fifth. That 3 is not being raised to the fifth power, only the x is. I can break it up a little bit further by bringing those powers down using this third property for logs. Again, I'm not finding the derivative, I'm simply just playing with the algebra so that when I do take the derivative, it'll be nothing but nice stuff. Derivative of a constant is 0, so natural log of 3, since it's just a number, when I differentiate it I get 0. Derivative of log of x is 1 over x, but I just have a multiple of 5 there. Derivative of log of x plus 2 is the derivative of the inside, well, which is 1 over x plus 2, but there's a multiple of 3 there. I can clean that up because right now I have something times a rational expression, something times a rational expression. I can just put those in the numerator and make it look like this. Not a bad derivative, but it took a lot of playing with the algebra up front in order to get there. Maybe you like it that way. Maybe you say, hey, I'm not comfortable with those properties. If you're not comfortable, then you need to practice because you should be comfortable by this point. If you're saying, you know what, I'd rather just do it directly, I'd rather just attack it using product rule and chain rule because I want to practice product rule and chain rule. Well, then yeah, be my guest, right? What you can do is take y prime. I'm going to do the problem twice, right? 2 different ways. You can take y prime and do the derivative of the inside. Now be careful, again, there's a function multiplied by there's a function. So you have to use product rule, which means the derivative of the inside is going to be 15x to the fourth. And I differentiate the first function, copy and paste the second function, product rule gets a plus. I keep the first function, I differentiate the second function, which means chain rule, because it is a linear function composed with a cube function. So the 3 comes down, I get x plus 2 quantity squared, and then chain rule says I multiply by the derivative of the inside. Lucky for me, the derivative of the inside of that is only 1. That's the derivative of the top times the bottom, because remember, I'm differentiating a logarithmic function. So I do the derivative of the top over the bottom. Now I've got a mess, and this clearly does not look like the same thing as that. Well, it's the difference between doing, most of the legwork up front, and then you don't really have much to simplify because you've cleaned it up already. Here, you're just simply taking the derivative and then waiting to clean it up. Now you have to clean it up later. Right? That is not a final answer. That is not worthy of a final answer. That's a mess. And if this was an algebra class, I would say you're not finished. But guess what? This is a calculus class, which is more than algebra, which means you're still not finished, right? You have to keep going. Because if you had to do it in the last class, guess what? You still need to do it in this class. There's no changing that. But it's not bad because I've got this plus, and I've got a common factor of 3. I've got a common factor of x to the fourth. I've got a common factor of x plus 2 squared, right? I've actually got 2 of those, so I'm going to pull out x plus 2 squared. And then it's going to leave behind that factor of 5 and that extra factor of x plus 2. And it's going to leave behind that extra factor of x and that extra factor of 3, and then the denominator is still the denominator. Kind of apologize there because it's a little squished in. And maybe we'll do this. Well, I did use those colors and I don't want to use them again. There we go. Right, so what's going to happen is I'm going to clean this up to try and see if I can get it to match this. Well, now I'm multiplying by 3 and dividing by 3 across top and bottom. I'm multiplying by x to the 4th, and then I'm dividing by x to the 5th. So one of those factors of x will remain in the denominator. I'm multiplying by an entire x squared, and then I'm dividing by, x plus 2 squared, and then I'm dividing by x plus 2 cubed. So again, just one of those factors of x plus 2 will remain. Now, I've really backed myself into a corner, but at least it's a lot neater now. 5x plus 10 plus 3x over x times x plus 2. So in total, I have 8x plus 10 over x times x plus 2. Now, I'm out of space, but do you know how to make this look like this? And the answer is yes, you do. Thanks to pre-calc, you learned how to do partial fraction decomposition. So you can do partial fraction decomposition and get these as your numerators. It's something you've already covered, so I'm not going to spend the time doing it here. There's no point in it. That's a perfectly good final answer. If you do it this way, I can follow your work and say you are correct. If you do it this way, I can follow your work and say you are correct. Again, that's why the final answer isn't worth all the points. All the points are in here, right? Your first step is where I first look. If that doesn't make sense, then there's no point in grading the rest of the problem because you started off with some false statement. But if you did it this way, I start here, right? If it makes sense, then I can follow it this way. If this makes sense, I can follow it this way. So that's why the final answer could look completely different, but have the exact same meaning. So do partial fraction decomposition on that, and you'll get this. Or if you get a common denominator here and put it all together as one rational expression, you would get this. Right? You can jump back and forth between the two. So when you look in the back of the book, it's not going to have two different answers. Right? Sometimes when you especially later when we get to integration, you'll see that there are different techniques for integration. You could have 5, 6, 7 different final answers, and they're all correct based on the correct process that you've done. So here, not so much, because when you differentiate, you usually get a unique derivative, which is not going to have too many different forms algebraically. But when you go backwards and integrate, whatever that means right now, when you go backwards and integrate, you'll see that the different forms can have the same meaning. So practice those log properties. They're never going away. And when it comes to log functions, if you'd like to just use those properties first, then making your differentiation easier, that's fine. Or if you'd like to just attack it directly, also fine. But I have to see which way you did it, and I have to follow every step. So again, just scribbling down one simple answer really isn't worth very much. You could find that answer on the internet in 5 seconds. I'm not grading the internet. I'm grading your work, your quality of solution. Let's say if y is equal to, let's take natural log of 4x squared times the square root of 3x plus 1, and divide that by x plus 2. Can we already use x plus 2? Let's change that. Let's make it x plus 7. I don't know, just to make it interesting. So, oh, and I think I wrote dy dx. For some reason today I'm on this dy dx kick. I think I wrote dy dx but wrote y prime. That's fine. That's the same meaning. let's see if we want to even attempt to do the derivative of the inside over the inside. If I differentiate a logarithmic function, I have to find the derivative of the inside, put it up top, and then take the inside, put it on bottom. Wow, that's going to be really complicated because the derivative of the inside needs product rule to differentiate the top, quotient rule to differentiate top and bottom, chain rule because I've got this weird radical and some polynomial inside, so it's a composition. So differentiating the top just right away is going to give you a mess, an absolute mess. So here's one of those situations where you're probably thinking, you know what, I'm going to go ahead and rewrite this first. I'll do a little bit of work up front so that the derivative is easier to find. So I've got multiplication of two things up top and then division of x plus 7 underneath. So I'm going to add these logs, 4x squared in the argument, plus, and while I'm at it, I'm going to write this as a 1/2 power, because I don't like that radical notation. And then I'm dividing all that stuff, so I'm going to subtract log of x plus 7. So I did sort of two things at once. I saw the actual division, so I broke this up with subtraction, but then when I break that up, I'll still have this product. So I went ahead and broke that up with addition. Now I can look at these and say, all right, I could go for these, but the derivative here involves this 1/2 power. This one is still that same multiple. 4 is not being raised to the power, so I think I'll go ahead and separate log of 4 plus log of x squared. And since that square is a power, I'm going to bring it down as a multiple of a log. Here, since that 1/2 is a power, I'm going to go ahead and bring it down as a multiple of a log. It doesn't have to be an integer power for me to do that, as long as it's a power, and that's what a square root is. It's just a square root, so it's a 1/2 power. Now everything is as expanded out as I can get it, so I'm going to go ahead and go for y prime. Derivative of a constant is 0, right? Natural log of 4, that's just a number. If I differentiate that real number, I get 0. Here I'm going to get 2 times the derivative of log x. That's 1 over x. I'll just multiply by 2. Here I'm going to get the derivative of the inside. Aha, there's a 3 there over the inside, but then I've got a 1/2. So it's going to be the derivative of the inside over the inside, but don't forget the 1/2 pops up. Minus, again, derivative of the inside, but in this case, derivative of the inside is 1, because that's just linear, over the inside. So don't just write x down there, make sure you write x plus 7 on the inside. All right, and that made the differentiation process super simple. So I do recommend doing that when you have a log function that's very involved like this. If you have this nasty style of logarithmic function, I recommend breaking it up like that first. It saves you a ton of work. Otherwise, you're more likely to make a mistake trying to product rule and quotient rule and chain rule, all that stuff in one big chunk. Right? It's like taking a bite that's way too big to chew. Right? Break it down into smaller bites. But let me show you a trick when you do have a function that looks like that is really nasty, that you want to get differentiated, and maybe it's just really gross and you don't want to have to differentiate it as is. Let's see if I can show you what I mean. Here we go. And the book refers to this as logarithmic differentiation, which is different than differentiating a logarithmic function. So the naming device they use might be a little confusing, but they call this process logarithmic differentiation. And if you are in the textbook, there are a bunch, like 39 through 50, I believe. Yeah, 39 through 50. And I'm just going to steal one of the even-numbered ones. That looks really gross. In this case, it is number 40. Looks really gross. If f of x is equal to e to the negative x cosine squared of x, that means cosine x times cosine x, over x squared plus x plus 1, So let's see if we can differentiate this. Gross, right? It is one of those nasty functions where I've got the product of two things, so I need to differentiate the top because quotient rule says first I do the derivative of the top. Oh my gosh, while I'm in quotient rule, I'm using product rule. All right, so that could be a little messy. But the book calls this logarithmic differentiation. So I'm going to write this as y instead of f of x just because it's a little easier to keep track of that way. And I'm going to rewrite it. I'm going to put some space there so that I can take the log of both sides. Right, if these two are equal, then log of those two things is also equal. Meaning now I can differentiate it, but in differentiating it, I have to differentiate both the left and the right, which we saw in the last section using implicit differentiation. But why differentiate this in its current state when I can use properties of logs now to break it all up and expand it out and make my life easier? So what I can do is say that this is the natural log of y is equal to the natural log of e to the negative x plus the natural log of cosine squared of x minus natural log of x squared plus x plus 1. All right, so I can do some breaking up like this. So if I want to rewrite it just a little bit more, this is e to the x to the negative power, right? It's actually e to the x downstairs, which means when I look at this, I can rewrite it as natural log of e to the x to the negative first power. Remember, power raised to a power, you multiply those powers, so that would be negative x. So I'm simply rewriting it in a way that I can bring that power down. Plus log of cosine squared of x is the notation for cosine of x times cosine of x. So I am in fact taking the cosine function and just squaring it. Remember, this one, there's nothing you can do with because of the addition, you're not allowed to break it up. And not everything has a square power, right? Remember the rule that said if the argument was raised to the power, you could bring it down as a multiple. There's no rule that says if you have addition and one of them is raised to the power, you can only bring the one and ignore the other one. That's not a rule, right? That's never going to work. And you can't break it up because of addition and subtraction. So in this case, we're just going to leave that and have to differentiate it as is. But at least now it makes things a little nicer because I have natural log of y. Again, I haven't differentiated anything. I'm just simply using my logarithmic rules to rewrite. So I get something that looks like this. Again, I can't do anything with the last piece. But we're almost there. We're actually almost ready to we are ready to differentiate because all this is as laid out as possible. Now, when I differentiate the left-hand side, remember your chain rule. I'm not differentiating just y to get y prime. I am differentiating the log of y, which is a function of x. So here's a function composed with another function. So I do have to be careful. When I differentiate log of y, I get 1 over y, but then chain rule says I must multiply by y prime. That's implicit differentiation that we're doing, which was the last section. Now, if I look at this, log of e to the x, the natural log of e to the x, this is just an identity for x because it's base e, and my argument is e to the x. Right? So I really can adjust this so that that power comes down. Maybe I could have done it in one step, but I really do just get negative x out of there. Right, so I would just get negative 1 as the derivative, or you can look at it as the derivative of the inside, which is e to the x, over the inside, which is e to the x. And I just have that negative 1 multiple. Here I have 2 times log of cosine. There is a function composed with another function. So I'm going to get the derivative of the inside, which is negative sine of x, over the inside, which is cosine of x, I do still have this multiple of 2 that I have to worry about. So that just sticks out front. Last one is minus, well, the derivative of the inside is 2x plus 1. Over the inside is x squared plus x plus 1. And that's pretty much fine. I would say maybe rewrite this one so that it looks a little bit better. Also, I haven't found y prime really. So I'm going to go back and say that y prime is, I have to multiply the left side by y to get these to cancel out, which means I have to multiply the right side by y. So I'm multiplying by y on both sides. Well, what is y? Y was that original big mess that I had, right? So I have to multiply both sides by that original y, aka my f of x that I called it. So I'm going to have, I'll rewrite it up there, I have a little more space. So I'm going to have y times negative 1 minus 2, and again I'm going to write this as tangent of x. I believe my brain said cotangent before. I'm sorry if I said that. So, final answer, we'll squeeze it up here, y times all of this mess. This was our y that we declared. So f prime of x is going to be equal to e to the negative x times cosine squared of x over x squared plus x plus 1 times negative 1 minus 2 tangent x minus 2x plus 1 over, oh, that's going to be a really tight squeeze there, x squared plus x plus 1. Like that. That is a minus in there. It almost looks like multiplication. You could factor that minus out of everything and maybe just write it way out front, and then you'd have pluses in there. But you can see that, of course, that was not a nice function, so of course the derivative was not going to be nice. But logarithmic differentiation allows us to take the log of both sides and then play with the properties, so at least the derivative is not so crazy. And then I just have to simply reinsert y, because again, I took the log of the function, so I'm differentiating the log of the function. I don't want the derivative of the log of f of x, I want the derivative of f of x. So I have to do that little last step, multiply by y on both sides to isolate y prime. Let's see what else we got here. This one, yeah, we'll just do one more just to have it done. I believe this one is on the study guide. I have a little mark next to it. Usually that's what that means. I put a little pen mark next to it. I usually put it on the study guide. And it asks us to find y prime and find y double prime. And they give you y is natural log of x over 1 plus natural log of x. So our goal is to find the first derivative and the second derivative. Okay, well, first of all, there's not really much we can do with this. Luckily, they are just log of x. They're not log of some crazy complicated expression. But because it is a quotient, I have to use the quotient rule. So we're going to do the derivative of the top, which is 1 over x, times the original bottom, which is 1 plus natural log of x. I'm going to omit the parentheses, otherwise it just might get a little complicated. And since there's not more going on in the argument, it's understood as just log of x. Quotient rule gets the minus, original top, times the derivative of the bottom. It's 2 terms. I differentiate 1, I get 0. I differentiate log of x, I get 1 over x. Then it's all over the bottom. Square. So here's the first derivative, but that's a little nasty. Since I do have to differentiate it again, I'm going to clean it up. Here's 1 plus log of x over x minus, here's log of x over x. And all of that is going to be over 1 plus log of x squared. Well, the numerators, the terms in the numerator have a common denominator of x. So I'm going to do 1 plus log x minus log x over my common denominator x. That is 1 over x. Still, we don't like to see it this way with the, complex fraction stuff. So I'm going to take 1 over x, since I'm dividing by x. I'm just going to put it down with the 1 plus log x squared. So here is y prime. Let's go ahead. I'm going to write y prime over here. Isolate it. Now that we've got y prime, we can differentiate it again to get y double prime. Again, it's a quotient. So what I can do is take quotient rule and say the derivative of the top. Okay, great. That's just 0 times the original bottom. Well, since it's 0, I don't care. Minus the original top. Well, it's just 1. Times the derivative of the bottom. Aha, the derivative of the bottom needs product rule because it's the product of two functions. So the derivative of the bottom is going to be the derivative of the first times the original second. I'm actually going to give myself some more space here. Move that arrow over too far. And I'm going to slide it over here. There we go. So again, derivative of the top 0 over the bottom, don't care, minus the derivative of the bottom, here's our product rule, which is the derivative of the first times the second, plus, this is going to be all subtracted, so I better use some parentheses, brackets, plus the original first, there's x, times the derivative of my second function has that square on it, so chain rule kicks in. The derivative of that second function is going to be 2, 1 plus log x to the first power, and then I need the derivative of the inside, which is 1 over x. All right, just differentiating the inside, 1 is going to go away, and derivative of log of x is 1 over x. Now I'm ready to finish off quotient rule by squaring the bottom. All right, so a little messy there, but, not too terrible, because that cleans things up. So it looks like y double prime is going to be, now watch that negative, right? Quotient rule gets a minus, and I always subtract this second piece, but this second piece needed me to expand out with product rule for the derivative, which means that minus gets distributed to everything here, not just the first term. So I'm just going to rewrite this as negative 1 plus log x squared minus, x's are going to cancel out. I'll get 2, 1 plus log x over. This x is going to be squared, and this 1 plus log x is going to be to the 4th power, because I'm going to square that square. Now, rather than squaring this out and doing all the terms that way, I have in the numerator common factors of 1 plus log x. I'm going to factor out the negative. I'm going to factor out the common 1 plus log x from both of these, which means if I factor out the negative, this will leave me with a positive 1 plus log x, because there's 2 factors there, and I only factored 1 out. And a positive 2, again, positive because I factored the negative out of both. I factored 1 plus log x out of both. It left behind 1 plus log x. I have to change that sign to positive there. X squared 1 plus log x to the 4th still on the bottom. But it does allow me to cancel one of these, complete 1 plus log x factors out with one of these. in the denominator, so I'll get a cube instead of a fourth power. And it also allows me to combine positive 1 and positive 2. I still have the negative. I'll have 3 plus log x, or log x plus 3, however you want to write it. But the negative does get applied to all of it. X squared never went anywhere. And 1 plus log x now gets raised to the third power in the denominator. So we've got y double prime. Let's isolate it. So again, logarithmic functions just getting thrown into the mix of all the other functions that we've already, or all the other properties, rules that we've already seen: power rule, quotient rule, product rule, chain rule, all that good stuff. Now we just have to know how to differentiate the log function as well as, trig functions, polynomials, rational functions, all that good jazz. So yeah, like I said, short section, but I did drone on. So practice these with the log functions now. Go back and look at some of the older stuff, like polynomials or trig functions. If you go back to that section where it says differentiate sine of x squared, try differentiating sine of log of x squared now, right? So, or mix it up. Try differentiating log of sine of x squared. Right? Try doing something like that, and it'll help you. It'll help you practice. Since we're only at 40-something minutes, if you're one of those people that says, "Yeah, I get it," then you're good. But I just set a function that I kind of like, so I'm going to do it. If y is equal to log of the sine of x squared, and find y prime. So I said it, let's do it. I have to differentiate the log function, which means I have to take the derivative of the inside over the inside. However, the derivative of the inside is a composition of two functions, the trig function and the square function. So I need chain rule there. So you can see that all these rules just start to stack on top of each other, right? So y prime is going to be the derivative of the inside. All right, let's differentiate the inside. I differentiate the outer function sine of x to get sine of x squared to get cosine x squared. But then the derivative of the inside is 2x. That's chain rule. So there's the derivative of the inside. I differentiate the outer function, rewrite the inner function, and then chain rule says multiply by the derivative of that inner function x squared, which in this case is 2x, over the inside. Because remember, I'm differentiating the log, right? That's the big boy log function. So I do the derivative of the inside over the inside. Now you can leave it like that, and there's really nothing wrong with that. But cosine x squared divided by sine x squared is actually cotangent of x squared. So you might see it rewritten like this, just to save space, right? There's nothing really wrong with writing it like that, but you might see it written like this just to save space. And generally, we like to see the numerical coefficient out front. The variable x would be probably most likely out front, so as not to be confused. If it's over here instead of up front, that looks messy, right? Especially when they drop the parentheses. So most likely you'll see it out front there. If it's me, I'll put the parentheses anyway, just to signify where it starts and stops. You should probably not write backwards. I get terrible X's when I do that. Okay, I'll stop there. So again, practice. Go back to some old stuff that you differentiated. Even go back to like Study Guide 1 and look at a couple of those random functions on there. And try just tossing in a log function and practicing that way. That might give you some good practice. So I'll see you in 3.7, where we'll get into a little bit more talk about rate of change, which is just more derivative stuff. So I'll see you there.